All right, here we go, moving into our last section of Chapter 4, which is Section 4.9 on antiderivatives. And our goal of differentiation is to find the derivative f prime of a given function f. Now, the reverse process, which is called anti-differentiation, is equally important. So, given a function f, we look for an antiderivative, which they refer to in this section as capital F, whose derivative is f prime. Need an E right there. Okay, so, or whose derivative is f. So here's kind of the definition that we're going to hold for just a little bit here. A function f is an antiderivative of f on an interval I, provided that the derivative f prime of x is equal to the function value f for all x in I. Okay, so it's almost kind of backwards. I wish they would use the capital F in a different way. They would switch that in lowercase f, but it is kind of a little bit backwards. So for example, if I let f of x equal x, then what is the f of x here is what they're referring to is the derivative of the original function. Well, the derivative of x is just a 1. We've worked on that many times. So therefore, this x is the antiderivative of 1. Okay, so this is the antiderivative right there. Okay, what if I give you this function? F of x equals x squared. And I ask you for what little f is, little f of x is, which is the first derivative of that function. Well, hopefully you're screaming at me that it is 2x. So therefore, x squared is the antiderivative of 2x. And if I have the original function of sine of x, then f of x, which is the first derivative here, is going to be cosine of x. Therefore, sine is the antiderivative of cosine. So this is the antiderivative. We are going backwards. So what we are doing is basically given all of these functions, you're now going to have to yield what the beginning function was in order for that to happen. Now, what if I modify this ever so slightly? What if I say here that f of x is equal to x minus 2? What is the first derivative of that function? Well, it is a 1, If I have this f of x is x squared plus 7, what is the derivative of that function? Well, the answer would be 2x. And if I give you this function where I have the sine of x minus 1, and I ask you what is the derivative of that function, well, the derivative of this function would be cosine, as I just take the derivative of sine because this derivative is 0. So now what I've just found is not only is this an antiderivative of 1, this is also an antiderivative 1. This is an antiderivative of 2x, and that's an antiderivative of 2x, and the antiderivative of cosine has two different functions here as well. Therefore, there are actually an infinite number of antiderivatives for each basic function that differs by a what? Well, all I did was add a constant to each one of those original functions, and so anytime that I have that differing by a constant, it will have the same derivative. Hence, this is what we refer to as a family of antiderivatives, because I'm going to let that capital F be an antiderivative of the little f on an interval I, then all the antiderivatives of our derivative, lowercase f, on some interval I have the form where I have the original function where we do plus c, where we refer to c as an arbitrary constant. Okay? So if we differ by c, because of this function, it is the same function, you're just having it differ by a +1 or a -3 or -10, then the antiderivatives are all vertical translations of one another. So if I had a family of functions, say x squared and an x squared minus 1 and an x squared plus 3, etc., then I could graph those functions. Obviously, here's my x squared. If I do that minus 1, I go down 1, and I have that function. And if I have a plus 3, then I end up having that quadratic function. So all of those would have the same derivative. Hence, that's what they refer to as a family of antiderivatives. So now, use what we know about antiderivatives in order to find out what is the antiderivative of the given functions. So that means, what did I have to take the derivative of in order to get a 3x squared? Well, notice I have a power, so this might be kind of a going backwards of a power rule. So what would capital F of x be? Well, if I bring the 3 out front and decrease that power by 1, originally I would have had that x cubed. So basically now I'm adding that back, but I have to kind of bring that 3 back up. And so remember, we are differing by a constant, so therefore that would be the antiderivative for all family of functions for that f of x of 3x squared. Now this, I have a negative 9x to the minus 10 if I do that. And remember, if I bring that negative 9 out front and decrease that power by 1, that means I have now a negative 10. So the original function that I have looks like x to the minus 9, but all of those that differ by a constant will have that same derivative. Now, what is the original function, f of t here, that whenever I take the derivative of it, I kick back a sign? Well, the derivative of sine is cosine, so that doesn't work. The derivative of cosine is negative sine. Well, I have sine, but I don't have the negative. So we can modify that by saying that this would be the negative cosine of t plus c, and that would actually give me the derivative to be equal to sine. So we're going to have some rules here in a minute, but we're going to discuss some notation first, getting you to think backwards, and this is going to be important for the last chapter. In Calc 1 here that we're going to get to with Chapter 5. And so you want to make sure that you're able to do that. So let's talk notation. The notation of d over dx of f of x means that I take the derivative of that function. Take the derivative of f of x with respect to x. Now, we need an analogous notation for antiderivatives. How do I go backwards? Well, we are going to use a symbol like this. It's kind of like an S or a little squiggle. This is what we refer to as the indefinite integral, or the integral symbol. And then there's going to kind of be two parts here. There's going to be a function, and there's going to be a differential, okay? So this is my function, and this is what we refer to as the integrand. And this is the variable of integration. Actually, more so this piece right here is the variable of integration. You're always going to have a d, but it could be dy, dx, dw, du, whatever the case may be. And this is also referred to as a differential from what we saw back in, I believe it was section 4.6. Okay? So therefore, this notation that I used here in integral form would look something like this. This is what I'm integrating. So I'm going to integrate 3x squared with respect to x. That's the variable that I'm integrating. That is equal to what our original function would look like, x cubed plus c. Okay? So that's one way to write it. If I want to write the integral of this, we would do the integral of negative 9 over x to the 10th dx. That's in terms of the variable we're integrating, and that was equal to x to the minus 9 plus c. And the last one, if I write it in my integral notation, that would be the integral of sine of t. Now, this time it would be dt, because I'm working in terms of t, is equal to the negative cosine of t plus c. And that's going to be our final answer in an interval form for that. Okay? Or an integral form, excuse me. All right, so let's get our rules. Here's our rules of integration that we're going to start with, okay? And we're going to use these quite a bit. So please make sure you're able to do them. In all cases, C represents the arbitrary constant. So I'm going to integrate some power, x to some power, and we're going to do that with respect to x, so dx. Now, here's the pattern. We have to bring that number back up front, but there's not a number up here. What we're going to do is that we're going to add 1 to the power, but divide by that new power. So I get x to the p plus 1 all over p plus 1 plus c, and we'll see some examples of that here in just a second. Where p, in this case, is not equal to -1, because if it was equal to -1, we would get 0 in the bottom, and that's bad. What if we want to integrate a constant times a function dx? Well, if there's a number in front of, say, a power, then we can, by rules of integration, bring that constant out front and multiply it by whatever you get when you integrate your function in terms of x. For real numbers, c. Okay, so this c is kind of different than the arbitrary c that we add to the end. The sum rule. If I want to integrate, say we have a polynomial that I'm adding or subtracting together, then if I have two functions that I'm adding together, and actually I'll just go ahead and put a minus in there too because this works for plus or minus, then that means I can integrate the first function in terms of x, add to that the integration of the second function in terms of x, and I'm going to put that minus there because that can work on plus or minus. So basically you're just integrating individually. You're just treating them as separate problems and working through that. And here comes our trig function. So I'm going to take the integral of cosine of x dx. Well, what did we take the derivative of to get cosine? We took the derivative of sine to get cosine. We just talked about the sine of x dx. We said that that was the negative cosine of x plus c. Don't forget your arbitrary constant. The integral of secant squared of x dx. What function did we take the derivative of in order to get secant squared? It was the tangent of x plus c. Analogous with that, we would have the cosecant squared of x dx. What did we take the derivative of to get cosecant squared? Well, it was actually a negative cosecant squared, which is actually this one's cofunction. And so that is cotangent, but I need a negative in there. So this one's going to be the negative cotangent of x plus c. Then we're going to turn to the integral of secant tangent dx. And what did we take the derivative of to get secant tangent? It was secant of x plus c. And the one that is similar to that would be the cosecant of x, cotangent of x dx. And that, just like all the other ones that start with c, will be a negative cosecant of x plus c. So when we were taking the derivatives, if I took the derivative of a function that had a c that it started with, the answer was negative when we looked at it as a derivative sense. When we are integrating, most of the time you're going to kind of see the positive of that, and your answer will end up being a negative if the answer starts with a c. So let's try a couple of these. Okay? So I want to integrate each one of these, and there's plus and minus here, so I can use my sum or difference rule and separate those up as I want to. And I also have some numbers in front of these functions. So I'm going to use also that constant multiple rule where I can bring that c out front of the integration. So this first one, and not all the time will you use this. Once you get used to integrating, you're just going to kind of do a lot of stuff in your head. But at first, we're going to take the 3 out, and I want to integrate x to the 5th dx. Here's my dx. I can kind of distribute to each one of those values. Then I'm going to add to that 2 times the integral of dx, which actually leaves me with kind of a 1 there, minus 5 times the integral of x to the 1/2 dx, and that's how I'm going to write that so I can use my power rule. So here comes the power rule. What did the power rule tell me to do? I'm going to, from x to the p, I'm going to add 1 to that exponent and then divide by the new power, basically, is what I'm going to do. So for this one, my power is 5. So when I add 1 to that, I get a 6. But I'm going to divide by that new power and get a 6 as well. Here's where things gets kind of tricky when you have to kind of simplify with your numbers. Oops, not a minus or an equals. Let's do a plus. Then I have 2. Now, what is the antiderivative? What did I take the derivative of to get 1? That is just my linear term of x. Minus, and here comes another power rule. This time it's going to be a little bit different because when I add 1 to that, add 2 over 2, I get x to the 3/2. Now, you can divide by 3/2, but I'm dividing by a fraction. A lot of people don't like to have that fraction in the bottom, so this is what we're going to do. If you have to divide by 3/2, that's the same as multiplying by its reciprocal. So I'm going to multiply by the reciprocal out front and get 2/3. Now, you can't be lazy and forget your arbitrary constant because when I integrate, I'm going to have a family of functions that differ by that constant. So let's simplify here. 3 cancels into 6 and makes that a half. So you can write as x to the 6th over 2. I like to bring the fraction out front as 1/2 x to the 6th. Then we have our plus 2x. And then when I combine 5 and 2/3, nothing will cancel, unfortunately, so that leaves me with a 10/3 x to the 3/2 plus c, and that's going to be our final answer for that. Okay? All right. Integration allows us to be able to break up our function a little bit or to modify our function before we do a little integration. And here, this is exactly what I want to do. With one term in the bottom, I can give an x squared to that term and an x squared to that term. You have to give it to both. If not, you've done it incorrectly. So I'm going to rewrite this function. If I have 19x's on top and 2x's on bottom, 2 of those are going to cancel. Or we can think about subtracting those exponents. 19 minus 2 gives me 4 out front, x to the 17th dx, minus, going ahead and breaking it up all at once here. I have a 5 I'm going to bring out front. Now, do the idea of subtracting those exponents. Negative 8 minus 2 gives me an x to the minus 10 dx that I have to integrate. Okay, so let's do that. Let's use our power rule. Add 1 to this power and divide by the new power. Minus 5. Add 1 to that. Be very, very careful. It's x to the minus 9. Divide by that new power, which is negative 9. And of course, do not forget your plus c. So at this point, I just now need to clean up my numbers. 4 over 18 is going to be a 2/9 when I reduce by 2, x to the 18th, minus 5 and a negative 9 actually makes that a positive 5/9, x to the minus 9, and then our plus c. And that would be your final answer at this point. Okay? All right, very good. We have a product of 2 binomials here. This, the easiest way to do, obviously we haven't gotten into chain rule substitution yet. That'll be coming in chapter 5. But here, the best way I can do it with the rules that I have in place is to do a little foiling. So in this one, we are going to FOIL this function and get what it's equivalent to. So I'm going to do my first terms here, gives me a 2z to the 3rd power. Outside is a minus 5z squared. Inside is a plus 2z. And my last term is a minus 5. And I'm going to integrate that with respect to z. So dz. Now, you might get to the point where you can kind of do this without writing it individually like I did up here. I don't expect you to write it every single time like this with everything separated. You should be able to realize I need to do this one, then go to this one, then do this one, and finish with that one. So let's see if we can do that. Now, you might not be able to do all this in your head at first, but you can do the power rule. Add a new power, add 1 to that, and divide by the new power. Minus 5. If I add 1 to that power, I get z cubed, divide by that new power 3. If I add 1 to that power, that gives me z squared all over 2. Minus, now when you get to a 5, remember that the derivative that I took had to be minus 5z. It was that linear term. So those you don't really have to do a power rule with. Just realize that that would be what it is. And don't forget your plus c. And at this point now I can go through and simplify all my numbers. This reduces to a 1/2 z to the 4th minus a 5/3 z cubed. Now the 2's are going to cancel, so I'm just left with a plus z squared minus 5z plus c, and that's my final polynomial for this function. Okay? Now the next one might be a little bit easier. Maybe I should have started off with that one. We want to integrate secant squared. Well, if I go up here, what is the function I took the derivative of to get secant squared? Boom, right there, tangent. And then I also have a constant. So the integral of this in terms of x is just tangent. This is a constant just like that minus 5. When I integrate, gives me a 2z. And don't forget about your plus c, and that's all we have to do on that one. Nothing to worry about on that. That one's pretty simple. All right, let's try this one. 3 different terms. We're going to have 3 different problems. One is a trig problem. Don't panic. I'm going to bring the 5 out front. And I'm going to add 1 to my power to give me a 2, divide by the new power, which is 2, minus 2. Now worry about this fraction. We had a fraction before. We have to add 1 to that, which would be the same as 3 over 3. So that actually gives me x to the 4/3. But instead of dividing by 4/3, let's multiply by the reciprocal, which is 3/4. Then, minus 3. Now, what is the antiderivative of sine? What did I have to take the derivative of to get sine? It was cosine, but cosine it starts with a c. Therefore, it's negative. And do not forget about that arbitrary constant. Do a plus c at the end of all of these indefinite integrals. All right, simplifying here gives me a 5/2 x squared. The 2 will cancel into the 4 twice, so that gives me a minus 3/2 x to the 4/3 plus, because I have double negatives there, 3 cosine of x plus c. Now, I haven't said it yet before, but I'm going to say it here. If you are wondering if you got the right answer, all you have to do is take the derivative of this to see if you get back what you started with. So sometimes they're pretty easy, other times they're kind of complex. But if you are ever wondering if you got the right answer, you have the power to figure that out, okay? All right, let's check out this next one, and it's going to be similar to our second one up there where we distributed our denominator to each one of the numerators to kind of simplify things ever so slightly. So I'm going to go ahead and integrate here. I'm going to have a 4 times a cosine of x, and this sine squared, I could put over sine squared, but I'm going to, for the time being, again, sometimes you got to mold your function how you want it. I'm going to write it as a sine times a sine. And then, when I do sine squared over sine squared, that's just a plus 1. So this I have to integrate with respect to x. So again, don't be lazy and leave off your dx. There's a lot of notation here that you want to make sure that you keep in. So, now, why did I do this and splitting across that sine squared? Because there wasn't anything of cosine over sine squared as a function that I can integrate with my trig functions. But if I split this apart and change it into things and think of this as 4 times this times a 1 over sine, I might be able to help myself out a little bit. So I'm going to write this as 4 times, this is cotangent of x. Cosine over sine is cotangent, and 1 over sine is actually cosecant of x. So if you change it into things that you know, plus 1 in terms of x dx, then this actually is one of our trig rules up top. And so cosecant and cotangent, it's reversed, but here it is, right here is the derivative of negative cosecant. So these first terms, this piece integrated is negative cosecant, but I have that 4. So that would be negative 4 cosecant of x. The integral of 1 is just, in terms of x, just an x, and then I cannot forget that plus c again. So many times students forget the plus c, so please make sure that that will not be you. Okay? All right, very good. Let's try our next page, which is getting us introduced into some differential functions, differential equations. Now, at the very first, it says an equation involving an unknown function and its derivatives is called a differential equation. Given this derivative, I want to find f. Notice here I've changed notation a little bit to this f prime of x. I want to go back to the original function that satisfies the derivative. Hence, this is the reason I hate that they use the little f here and the capital F on the definition that we had on the first part of our notes, but make sure that you watch your notation and you know what it is. So, if I want to go from f prime to f, we have to integrate or do anti-differentiation. So what would f of x look like? What is the derivative, or what is the function I took the derivative of to get 2x? Well, that has to be x squared. Why? I can add 1 to that power and divide by 2. The 2's are going to cancel and leave me with an x squared. Then I come to a 10, so that was the linear term, plus c. So we've talked about these family of functions, that this is what it's going to equal to, but, excuse me, in most practical cases, a differential equation is accompanied by an initial condition that allows us to determine the c. So not all the time will we leave our answers with a plus c, because given an initial condition, I can actually plug that in now and figure out what that c is. So let's do that. I want to find the solution of the following initial value problem solving a differential equation. So I'm going to first integrate this piece here to find f of x. So f of x is going to be the integral of x squared minus 2x dx. Now what is that? I'm going to add 1 and divide by the new power. So I get x cubed over 3, which is the same as 1/3 if I want to bring that out front. So I'm going to kind of show you some tricks of trades and stuff of things to help you out. You can do it multiple ways. The derivative that I get here is 2x. What did I have as my original function to get a derivative of 2x? Well, we just did it up there. It is an x squared. And then I have plus c. Now, this is the case where here this comes into play. This is the x value that I'm given, and this is the y value, which is the same as the f of x in my equation. So in order to find c, I better know these x's and I better know the f of x. Well, I do. Here's the f of x. It's 1/3. Is equal to, x is equal to 1 that I would plug here and here. So I get 1/3 times 1 cubed minus 1 squared plus c. Now, let's simplify. I'm going to keep this as 1/3. Now this becomes 1/3 minus 1. 1/3 minus 3/3 is a negative 2/3 plus c. And then I can solve for c by getting rid of this. Well, if that's a minus, I'm going to add it to the other side. So c is equal to 1/3 plus 2/3 is 3/3, which is equal to 1. Therefore, our final function, f of x equals 1/3 x cubed minus x squared plus 1 is my final answer, because I take that c and I plug it in and simplify for what I have. Okay, very good. Let's try another one. This one, before I integrate, I'm going to change this as to 1 minus t to the minus 2. So if you have anything in the denominator, bring it up with a negative exponent. So f of t in this case is going to be found by taking the integral of this, which is t, minus, using power rule, I would add 1 to that. When I add 1, that gives me t to the minus 1. But then I have to divide by that new power. When I divide by negative 1, the value really doesn't change, but with that negative and this negative, that ends up being a positive. Now you can write that out if you want, but then don't forget your arbitrary constant either. So there's, like I said, there's a lot of things that could be in your head a little bit. So let me do that without t minus, this would be t to the minus 1, divide by minus 1, plus c, and this piece right here is what's going to make that to be a plus in my function. So I'm going to write this as f of t is equal to t plus 1 over t plus c. And now I'm going to use my initial condition that they gave me. This is the y value. And I'm going to plug t equaling 1 in here and here. So basically I get 1 plus c. This one's not too bad to solve. This gives me a 2. When I subtract it over, c is negative 2. Therefore, f of t is equal to t plus 1 over t minus 2, and I have just solved that differential equation given that initial condition. Okay? All right, very good. So I hope you're still with me. If you have any questions, please don't hesitate to ask. Make sure that we are going to now, with the last part of this note sheet, reconnect with our motion problems that we've done in previous chapters. And so antiderivatives allow us to revisit the topic of one-dimensional motion, introduced in section 3.6. Now I remember the relationship between position, velocity, and acceleration. If I let S of t equal the position, what did I have to do to that position or the height, whatever we refer to it as, to get the velocity function? Well, I had to take the derivative of that. So the first derivative is equal to v of t, normally is what we talked about, and that referred to the velocity of that function. Now, if I take a second derivative of the original position function, we referred that to, as the first derivative of the velocity, which was also referred to as a of t for the acceleration of that function. Okay? So in a sense, when we're working with these antiderivatives, now instead of starting at our position and going this way with our derivatives, we are going to start here and go backwards to find our position. So a of t is where we're going to start, and that again is your acceleration. Now, most of the time I will tell you that the acceleration with these motion problems is dealing with the speed or the acceleration due to gravity when we're doing projectile motion stuff. So watch out for that. Now, if I integrate a of t dt, I go from acceleration and I integrate or take the antiderivative, I get to my velocity. So that's equal to v of t, which is the velocity. And if I then take the integral of v of t dt, going backwards from the velocity back up here, tells me that I get back to s of t, which is the position function. Okay? So let's see if we can kind of work through a couple problems here with this one-dimensional motion to see if we can work through that. So, along with some given initial conditions, these functions can be determined by antiderivatives. So, given the velocity, can I find the position? I have the velocity function here, and they give me an initial condition for the antiderivative, which is the position, so that I can determine that plus c. So let's rewrite v of t. V of t I'm going to write as 4t to the 1/2. And if I integrate v of t dt, that gives me s of t, which is what? Well, here we're going to use a power rule. So I'm going to keep the 4 out front. I'm going to end up adding 1 to this, which is adding 2 over 2. So that gives me t to the 3/2. But then I have to divide by that new power, and since it's a fraction, I'm not going to divide by that fraction. I'm going to multiply by the reciprocal, which is 2/3. Now, do not forget that plus c, okay? So what happens here now is that I can simplify this a little bit and say, okay, s of t, let's do the 4 times the 2/3 to get an 8/3, t to the 3/2 plus c. And this is the chance that I get to use my initial condition and figure out what that c value is. So here, this is what my y value is. So I'm going to plug in 1 equals 8/3 times 0 to the 3/2 because my x value is 0 plus c. Well, it's really nice when things are 0 because that's going to go away. Therefore, my c value is equal to 1, making my final position function s of t equal 8/3 t to the 3/2, take out the c, plug in a 1, and that is your final answer. So again, going backwards, get used to that power rule. You'll see yourself doing a lot of shortcuts with that to save yourself some time, and that is A-okay. All right, our next example is going to flow through the rest of the notes. So we're going to say, neglecting air resistance, the motion of an object moving vertically near Earth's surface, moving vertically near Earth, so it is going down and decreasing, is determined by the acceleration due to gravity, which is approximately 9.8 meters per second, but the direction is negative. So it's going down, so this acceleration is going to be a negative 9.8. Suppose that a stone is thrown vertically upward at t equaling 0 with a velocity of 40 meters per second from the edge of a cliff that is 100 meters above the river. Find the velocity of the object if t is greater than or equal to 0. So first off, with this piece here, anytime that you are working with a projectile, its acceleration is going to be due to gravity. Now this is in meters, so it's negative 9.8. If we were in feet per second, it would be a negative 16. Okay, so make sure that you know that, or we would reference that for you. Now, we also have a couple initial conditions here that we have to pick out of our problem. So I know that the initial acceleration is negative 9.8, but the initial velocity when t equals 0 is at 40. So I'm going to represent that by the v of 0 equals 40. Here's my initial velocity when t equals 0. Now they're also going to give me an initial condition possibly of my position, in which they did. At t equaling 0, we're on the edge of a cliff that is 100 meters above the river. So at t equaling 0, the height of that object is at 100. Now why do we need those? We need those to be able to find the velocity function completely without a c and the position function completely without a c. So if I need to find velocity, and I'm doing some antiderivatives, this is the only given information that I have at this point. So if a of t is negative 9.8, the velocity in terms of t is going to be integrating that function in terms of t. Now, you can pull the negative 9.8 and just integrate dt. That's the case where, well, what did I get to take the derivative of in order to get negative 9.8? Well, that's negative 9.8t. Plus, that arbitrary constant will be kind of the generic form of the velocity until I use this initial condition now to find c. So I'm going to plug 40 in for my velocity equals, plug in 0, 0 again is so nice, negative 9.8 times 0 plus c, well again, that term goes away, therefore c equals 40. So here's my velocity function. Negative 9.8t plus 40 is going to be my velocity function for any t greater than or equal to 0. So now what I want to do is to be able to use that to find my position function, because if I start with acceleration, I integrate to get velocity, and if I integrate velocity, then I get position. So my position function, s of t, is going to be the integral of v of t dt. And what is that? Well, that's equal to the integral of what we just found, negative 9.8t plus 40, and I'm going to do that with respect to t. That's just the variable that we're using, okay? All right, very good. So let's do a little power rule. Let's bring that constant out front. I'm going to add 1 to this power to give me t squared over the new power, which is 2, plus, here's my constant. When I integrate a constant, I get back 40 times t, that's that linear term, plus c. And this is what s of t is going to be equal to generically. Now, we can simplify that ever so slightly. I can take 2 into that 9.8 and get negative 4.9 t squared plus 40t plus c. So, when we were working with these problems back in section 3.6, what you were given was a function like this, and you didn't know necessarily that this was the acceleration kind of due to gravity in the end, and that this is your initial velocity. So make sure now you're finding those functions, which is kind of nice. So now we have to determine what c is, but right now we're given this initial condition that we want to plug in, okay? So I'm going to plug 100 in for the original position, but notice if t equals 0, this goes away and that goes away. So I get 100 equals 0 plus c, which means that c is equal to 100. Okay, so basically I'm going to substitute that back in. S of t is negative 4.9 t squared plus 40t plus 100. And that will be our final position function for this particular problem. Okay. Now, continuing with this idea, so we'll need possibly some of these functions Part C here asks us, find the maximum height of the object above the river. The maximum height. So here I'm on this cliff that's 100 feet or 100 meters high. I'm going to throw it vertically and it's going to come down to the river. I want to know its maximum height here. So, going back to the idea when we were working with this before, the maximum height occurs when I have tangent lines that end up becoming a horizontal tangent at that point. So here, I want to know when the velocity is equal to 0. So I'm going to go back to part A on the reverse side and remember that negative 9.8t plus 40 was my velocity function, and I'm going to set that equal to 0 and solve for t to help me out. So I get negative 9.8t equals negative 40, and when I divide by negative 9.8, you do get a decimal of approximately 4.08 seconds. So that's when the maximum height occurs. But notice the question said find the actual maximum height. So I know a time at which it occurs. If I'm looking for height, aka that is the position function. Okay? So we need to plug that into S. So we need S of 4.08, which is negative 4.9 times 4.08 squared plus 40 times 4.08 plus 100. And this is the time that I encourage you to go to your scientific calculator or to your graphing calculator and throw that all in and kick out 181.6 meters as my final answer for that question. So we've kind of done these questions before. It's just making sure that you remember the stipulations and what conditions need for that. All right, and our last problem is with what speed does the object strike the river? So here, we're at time equaling 0. I'm going to have a certain point at which it's going to strike the river. Now, if I were to extend that parabola down, notice there's 2 points at which my height, or my S of t, is equal to 0. That's when we're going to strike the river, and that's going to be some important information to help me figure out the answer to this question. But let's revert back to the speed. Reminding ourselves from chapter 3 what speed is. Velocity includes speed and direction. Speed is just the number behind that. So if you recall, speed is equal to the absolute value of our velocity function. Now, we want to know the time when S equals 0. That's what we need to find out so that I can plug it into my velocity function, which is this piece right here, and take the absolute value of that. Now, here, let's talk about that S of t. From the previous page, flip it over if you have to. Here is S of t. Negative 4.9t squared plus 40t plus 100. I want to know when that is equal to 0. Now, unfortunately, there's nothing we can take out except for maybe a negative. You can take the negative out if you want. But you do not have anything that you can divide by. There's no 2 in common, no 5 in common, nothing. So I'm going to use this as my A, my B, and my C. We can't factor this, but we can use the quadratic formula. So I wanted to do this problem for you, so in case things don't factor, you can use the quadratic formula. So that was x equaling negative b, which was negative 40, plus or minus the square root of b squared, which is 1600, so 40 squared, minus 4 times a times c. Now, do you see this negative right here? Be very careful, because when you multiply all the way here, this is going to be negative, which in turn makes that a positive. All over 2a, so 2 times negative 4.9. All right, so if I'm going to simplify this, I'm going to get x equals negative 40 plus or minus. Remember, multiply this, and you're going to add to 1600, gives you 3560, all over negative 9.8. Now that one's not so nice, it's not so pretty. So in your calculator again, negative 40 plus this radical, divide that by negative 9.8. You should get the answer of negative 2, this one is going to be, the answer is going to be 10.17 for the plus version. And then the minus version of negative 40 minus this, divide by that, is going, I might have them reversed. Anyway, the two numbers that you get, sorry, I think I do have them reversed again. When you plug those values in, negative 40 plus root over negative 9.8 and negative 40 minus root 3560 over negative 9.8, these two are our times at which our height is equal to 0. Well, if this is a time, and actually I should probably put a t here to represent our time, since I have a t up here in my equation. Doesn't make sense to have negative time, but in our picture, hopefully it does make sense to you. This is the negative 2.007 right here, because this is when time equaling 0 is when we're at the height of 100. So now, the time that I'm going to hit the water is at 10.17. So going back over here where we're saying, okay, we need the speed at when we hit the ground or hit the water, I'm going to find the absolute value of v at 10.17, and that's going to give me my answer. So I do the absolute value of negative 9.8 times 10.17 plus 40, because if you recall, that is my velocity function that I got right here and also in part A on the reverse side. And when I do this, I get the absolute value of negative 59.667. And when I round that, take the absolute value, I end up getting 60 meters per second is the velocity. Now, or is the speed, excuse me. If I would have asked for the velocity, it would have been this negative 59.667. And would it make sense that it's negative? Absolutely, because it's coming down to the ground. That's the direction part. Negative means it's going down to the ground. So the speed is just a 60 meters per second. And that there is the end of chapter 4. And we're going to move on to chapter 5, which we get to do some more of this integration. And we'll get some application of the integration, and we'll get some more techniques to figure out how to do it for more functions. So until next time.